Well, welcome to QOD number 33 video, and I'm starting in an unusual spot, which is not with a PowerPoint slide, but with this, actually, this is a worksheet from my biology class, and it just so happens that we're talking about equilibrium in there right now as well, and that has to do with diffusion of things across membranes. And so the idea here is that if you have, say, these little dots, which I would either represent like water molecules or oxygen molecules or something, their net movement is from the outside to the inside because there's a higher concentration of these little dots on the outside than there is on the inside. But you'll notice that there is movement from the inside to the outside as well. As long as there's a difference in concentration, there will be a net movement in one direction. But once it reaches a situation where the concentration of the dots inside is equal to the concentration of the dots outside, then they'll be going in and out at the same rate, and you will have reached equilibrium. And so I just say that to say what's true of physical processes is also true of chemical processes. If you have a reversible chemical reaction, then it will reach equilibrium when it reaches a point at which the rate of the forward reaction is equal to the rate of the reverse reaction. And that's just important to keep that in mind, that that's really at the core of equilibrium. But let's actually get to the slides. Because in order to be able to have a forward and reverse reaction occurring at the same time, you need a reversible reaction. And up until now, we've just been thinking in terms of reactions that essentially go to completion. And one good example of this that I had on the board previous to this recording this video was the combustion of methane, which has a delta G value of negative 820 kilojoules per mole. And we talked about the fact that the rate of the reverse reaction would be so infinitesimally small that it essentially can't occur. Only the forward reaction can occur. And so, but if you have something where the reactants and products are reasonably similar to each other in potential energy, this is what's called the Haber process, which is the synthesis of ammonia from nitrogen gas and hydrogen gas. Well, the delta G for this reaction it's not zero, but it's a lot closer to zero than this. It's within the range of what a typical activation energy barrier would be, which means that although the forward reaction is faster than the reverse reaction, they can still both occur. And so the thing to think about in this case then is if I put some ammonia and some hydrogen together and some nitrogen and hydrogen together and let them react to form ammonia. Initially, I only have reactants for the forward reaction, and so it is the only thing that will occur. But as the reaction progresses, I begin to build up product. And if I begin to build up product, well, now I have reactants for the reverse reaction. And so as this goes along, the rate of the forward reaction will decrease while the rate of the reverse reaction increases until they reach some point at which they are occurring at the same rate. And so let's think about this in terms of a real substance here. They're showing you just a modeling image of frozen dinitrogen tetroxide, and so they're showing you in a nice orderly way because that's frozen. If I let this warm up and so that it goes from being a solid to being a gas, it will actually start to decompose. The dinitrogen tetroxide molecules will start to fall apart into nitrogen dioxide molecules. And you can tell that because nitrogen dioxide is brown, whereas dinitrogen tetroxide is colorless. And eventually you will reach a point at which the brown color just reaches a certain intensity and stops getting any darker. At that point, if you could actually look in at the molecular level, you would see there's still a combination of dinitrogen tetroxide and nitrogen dioxide molecules. But it becomes a static situation, an equilibrium situation in which the forward reaction of decomposition is occurring at the exact same rate as the reverse reaction of combination. And if we looked at that graphically, this is not plotting concentration versus time. This is plotting rate versus time. And initially, there is no rate. Initially, because there's only starting materials to begin with, the reverse reaction is not occurring. So it has a rate of 0 at time 0. But as the forward reaction occurs, that builds up concentrations of reactants for the reverse reaction, and so its rate starts to go up. Eventually, they will zero in on each other and reach a point at which both reactions are occurring at the same rate. And when they're both occurring at the same rate, then you've reached equilibrium, and there's no change in there's no net change in concentration of the reactants and products after that point. This is the reaction we're talking about, the decomposition of N2O4 into nitrogen dioxide. And as I mentioned also in class, this has a very small value for delta G, which means that the forward and reverse reactions almost proceed at almost the same, almost are as, I'm sorry, the values of the rate constant for the forward and reverse reaction are going to be very, very similar to each other, because the difference in potential energy between the reactants and the products is almost insignificant compared to the size of the activation energy barrier. Now you'll see in this graph that the reactions are occurring at the same rate. That doesn't mean that you have the same concentration of reactants and products in solution. It's rarely the case that at equilibrium you have exactly the same concentrations of reactants and products in solution. You'll see if we plot concentration versus time, once again, the reactant concentration goes down until you reach equilibrium. The product concentration goes up until you reach equilibrium. But those concentrations are not the same as each other. They do remain constant after equilibrium is reached. What is equal to each other at equilibrium is not the concentrations of reactants or products, but the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, well, let's talk about what's called an equilibrium constant, because we can define a quantity known as the equilibrium constant. Well, let's take a look at both the forward and reverse reaction. The forward reaction occurs in a single step. It is the decomposition of one molecule to two molecules of NO2. It is unimolecular, and that's the entire mechanism. So I can write this rate law. Rate is equal to K for the forward. We call this K sub F because it's the rate constant for the forward reaction, times N2O4 in its first order, because this is a unimolecular single-step mechanism. The reverse reaction turns out to be a bimolecular single-step mechanism. And so I can write this rate law for the reverse step, that the rate of the reverse reaction is equal to Kr, which is the rate constant for the reverse reaction, times NO2 squared, because it is a bimolecular single-step mechanism. Now, if I define now at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, and therefore I can simply substitute these in. The rate of the forward reaction is equal to Kf times N2O4 to the first power. The rate of the reverse reaction is equal to Kr times NO2 to the second power. Now I define the equilibrium constant as being equal to K forward over K reverse. And so I'm simply just doing some algebra here to get both of my K values on the same side of the equation and all my concentration terms on the other side of the equation. And what you will see is that the value of the equilibrium constant, which is equal to the value of the ratio of Kf to Kr, is equal to NO2 squared over N2O4 squared. So let's just go back and say we got this. We use this algebra to get this ratio, Kf to Kr. Kf times N2O4 is equal to Kr times NO2 squared. Using algebra, we get to this expression. If we define this ratio, Kf over Kr, as big K EQ, then this is the equation that we get. Well, this is a specific case, that is for this reaction, of what's known as the law of mass action. And the law of mass action simply says that for a generalized reaction in which A plus B goes to C plus D, the capital letters represent the substances. The lowercase letters represent their coefficients in the balanced equation. For any generalized reaction like this, the ratio of products to reactants at equilibrium is always going to be this. The product of the concentrations of the products raised to the power of their coefficients in the balanced equation, divided by the product of the concentration of the reactants raised to the value of their coefficients in the balanced equation. You may wonder why this is called Kc, and over here this was called Keq. They really mean the same thing. Keq means equilibrium constant. Kc, anytime you got a capital K, that means equilibrium constant. The subscript C means that it is based on concentration of reactants and products. Later in this chapter, we'll talk about another equilibrium constant called Kp, which is based on partial pressures of gases in solution. But Kc, when you see Kc, you should simply think of it as meaning the same thing as Keq. The key thing is that if it's an equilibrium constant, it's going to be a capital K, and if it's a rate constant, it's going to be a lowercase k. All right, well, this is what's called the law of mass action, and this was worked out by some scientists back in the 19th century, that no matter what concentrations of reactants or products you start with, they will eventually come to some equilibrium if it's a reversible reaction, and the ratio of their products to reactants will always fit this generic equation. So let's try some examples of doing this. Let's take an actual reaction. This is something we'll study a little bit later when we get to acids and bases, which is the next chapter. But here is remember, a hydrofluoric acid is not a strong acid, and so it only ionizes a little bit. And this would be the equation for the ionization of HF, that it goes to H plus F minus. But this is a reaction that actually favors reactants. But there are some products present in solution at equilibrium. How would you write the equilibrium constant expression for this? Well, if you'd like, you can turn the video off, pause the video, think about what that's going to be, and then turn it back on. So the Kc, that is the Keq based on concentration, the Kc for the expression for this reaction is going to be the concentration of H plus times the concentration of fluoride over the concentration of HF, because it's the product of the products raised to the power of their coefficients in the balanced equation, and in each case here the coefficient is 1, divided by the product of the reactants. Well, there's only one reactant, so there's no product, it's just its own concentration, raised to the power of its coefficient of the balanced equation, which is 1. So there's a fairly straightforward equilibrium constant expression in which all of the coefficients are 1. Let's try another one. Here's the reaction that we did in the iodine clock reaction. So try writing an equilibrium constant expression, a Kc expression for this reaction. Well, that Kc expression is going to look like this. It's going to be the product of the product concentrations raised to the power of their coefficients in the balanced equation. So that's going to be sulfate to the second power, because that coefficient is a 2. It's going to be times iodine to the first power, divided by persulfate to the first power, because that's got a coefficient of 1, times the concentration of iodide squared, because that's got a coefficient of 2. Let's try one more. I talked earlier about this Haber process, which is the synthesis of ammonia from nitrogen and hydrogen. Try writing a equilibrium constant expression, a Kc expression, for this reaction. Well, there's only one product, although there's 2 moles of it, and therefore we raise it to the second power. So it's going to be the concentration of ammonia squared, divided by, now, the product of the concentrations of the reactants raised to the power of their coefficients in the balanced equation. So it's going to be times N2, divided by N2 times the concentration of H2 cubed, because that has a coefficient of 3 in the balanced equation. So that's something that you would be able to expected to be able to do on a QOD, is look at a balanced equation and write the equilibrium constant expression. Now, here's the thing about equilibrium. Because we're talking about a reaction which can occur in both the forward and reverse direction, you can reach equilibrium from either direction. And so if you go back to the reaction in which we are watching N2O4 dissociate or decompose into NO2, we can start with all product and no reactant, which is what experiments 1, 2, and 3 are. Or we can start with all reactant and no product, which is what experiment 4 is. And then we allow it to reach equilibrium, look at what the concentrations are, and then plug those into the equilibrium constant expression, which would be NO2 squared over N2O4, because the coefficient of NO2 in the balanced equation is 2, and it's the product. So if we look at the ratio of the square of NO2 to N2O4, we get the same number every time. No matter what concentrations we started with, they're going to reach an equilibrium, which, if you plug them into that expression, will give you the same value for Kc, which for this reaction at 100 degrees Celsius is 0.211. What's interesting to note, and this is simply taking these data from experiments 3 and 4. In experiment 3, you start with 0.04 molar NO2. In experiment 4, you start with no NO2, and instead you have the reactant. Regardless of whether you start with all product present and no reactant, or all reactant present and no product, they wind up coalescing at the same concentration, which is the equilibrium concentration. You'll see at equilibrium, regardless of, in both experiments 3 and 4, you wind up with the same concentration at equilibrium for the NO2. Here's another example of it. This is that Haber process, again, in which we're combining nitrogen with hydrogen to make ammonia. You can start with only reactants, like this one does, in which you've got hydrogen and nitrogen present in the beginning and no ammonia, and it will reach equilibrium. Or you can start with no reactants present and only product present, that's the ammonia, and let that go, and it will reach equilibrium from the other direction. So it doesn't matter whether we start with a combination of the reactants or we start with the combination of the product or products, we will have the same, when they're done, when it reaches equilibrium, whatever those equilibrium concentrations are, if we plug them into the equilibrium constant expression that we wrote earlier, we will wind up with the same ratio. So just the last slide would be to say, what are the minimum requirements to reach equilibrium in terms of what do you need in terms of having components of the reaction present? Because what this is showing you is you don't have to have any product present as long as all the reactants are present. You don't have to have any reactants present as long as the products are present to reach equilibrium. What do you need? The minimum requirement to reach equilibrium is that you start with all of the reactants present, or you start with all the products present. Anything else that's in there on top of that is fine. So if we look at this reaction, the last last reaction we're going to look at, chlorine plus 2 NOBr gives me 2 NO plus 2 ClBr. If I've got chlorine and NOBr present, I can reach equilibrium because I've got both reactants present. If I've got NO and ClBr present, I will reach equilibrium. I can reach equilibrium because all the products are present. Okay. If I've got both reactants plus one of the two products, I can reach equilibrium. If I've got both reactants and both of the two products, I'll reach equilibrium. If I've got both products and one reactant or the other, I will reach equilibrium. The only instance in which I won't reach equilibrium would be if I only had one reactant and one product present. So let's say I have chlorine. I take chlorine and NO and I put them into a flask. I cannot reach this equilibrium. The reason is because I only have one of the two components necessary for the forward reaction. which is chlorine. I only have one of the two components necessary for the reverse reaction, which is nitrogen monoxide. And so neither the forward nor reverse reaction can occur, and therefore I can't reach equilibrium. But if I have both reactants, the forward reaction will start, and once the forward reaction starts, it generates products, which are the reactants for the reverse reaction, and I will reach equilibrium. So the key takeaways from this is just to understand what equilibrium means in terms of we reach equilibrium when the rate of a forward and reverse process are occurring at the same rate. You should be able to write an equilibrium constant expression from a balanced equation, and you ought to be able to answer this question of which components of the reaction are minimally necessary in order for me to be able to reach equilibrium based on the combination of those components. Okay, thanks so much for watching, and look forward to seeing you at the QOD.